Thank you, Mike, again. Okay, so our next speaker is Yicheng. Okay, sorry. All right, stage is yours.
Thank you. Good morning, everyone. Thank you for being here. And also, I'd like to thank Joe, Avishai, and Colin for organizing this fantastic workshop. So it's always good to be back to Santa Cruz, and I cannot believe it has been 11 years since I first attended this workshop. So today I'm going to talk about Starburst and Quenching of low-mass galaxies. And here, low mass means stellar mass less than 10 to 9.5. And I call it intermediate redshift. Perhaps I should call it a low redshift today. But intermediate, just to remind you that actually the cosmic age, the age of the universe is about several billion years. It's almost half of the age of the universe. So it's good to call it intermediate still. So I'm going to, as you can see, I'm going to talk about the two stuff, starburst and quenching. So during my talk, I'm going to make a sharp U-turn. So just keep your safety belt buckled. And those are my collaborators. Most of them are coming from the Candles team and Hello 70. Okay. So why should we care about low-mass galaxies? So we have heard a lot of talks yesterday, and we will have some more today. So low-mass galaxies, there are many reasons that why we should care about low-mass galaxies. Here's just one. So low-mass galaxies can help us connect. I don't know what's going on. Can help us connect baryons to dark matter. And the example is the core problem, and we heard about solutions from yesterday and on Wednesday. So here is a nice summary plot from James' review paper in 2017. So I'm not going to detail to repeat the problem and the solution, but the point I want to mention is that this talk I will focus on so-called bright dwarf galaxies, and this is the regime where we need the most prominent baryonic effect to solve the corresponding core problem. And we heard about starburst from the day one of this workshop, and this morning again. So starburst is very important ingredient in this picture to solve the corresponding core problem. But we should ask a question. Okay, observationally, those real dwarf galaxies, are they really burst? So if they are not, and the assumption in your model is not correct. And if they are they bursty enough to solve the corresponding core problem? Okay. Now the question is, observationally, how can we measure the burstiness of dwarf galaxies? We just heard a nice talk from Jenny about how to measure burstiness from massive galaxies. But dwarf galaxies, they are different. They are faint, they are small, and they are hard to observe. So we probably cannot do the full range of SED fitting on them. But here is a quick way to measure burstiness in dwarf galaxies. So basically, we use two star formation rate indicators. One is UV, and the other one is H alpha. UV is tracing O and B stars on a time scale of about 100 million years. And the H alpha is tracing O stars. Then it has a shorter time scale on 10 million years. So now if you have a population of galaxies, and if you assume all the galaxies in your population are the same, and they just at different evolutionary stages, and if you look at the average star formation rate estimated from UV and average star formation rate measured from H beta, you take the ratio. So if the star formation history of low-mass galaxies is bursty, this ratio, H beta or H alpha, doesn't matter, natural emission line should be fine, should be less than 1. If the star formation history is smooth, this ratio average should be equal to 1. Okay? So now this gives us a very nice way to measure star formation burstiness. And I'm jumping quickly to the result because this is a result from my paper several years ago. And you see the ratio from file and also the ratio from local star-forming galaxies from WISO-SO 2012. And the sign point is the ratio from dwarf galaxies at the redshift 0.5. And the ratio matches the file. This is file 1. We probably should do the comparison again for file 2 and file 3. Observation matches the simulation very well at that time. Okay, so this is nice. Low mass dwarf galaxies, they are bursty. But, not but, okay, let me finish this part. So we also measured what we call the burstiness, which is basically how many stars were formed in the bursty phase and how many stars were formed in the smooth, steady star formation phase. And we used a model from WISO-SO 2012, and then we measured this burstiness, which is basically the duration of the burst times the amplitude of the burst and divided by the period between two bursts. And this ratio at redshift 0.5 is higher than the value at local universe. This is 1, meaning half of a star formed in burst and half of the star formed in continuous, steady star formation. So this, again, this is result in 2016. Okay. So now, let me go to tell you something we have to be careful. I said the H alpha to UV ratio is very nice, but there are a few problems. So because the variation of nebula to UV ratio can be complicated. It depends on the IMF. We just heard the story of IMF. Loss extinction, ionization escape fraction, even binary stellar evolution, sample completeness, and the time scale of indicators. Okay. So here is plot from Rizzo et al. 2022. And they find this ratio has no correlation with age and the star formation rate density. And of course, this is at higher redshift. And those are for a little bit high mass galaxies. Okay, so we need an independent check on the starburst. So recently, my student and I are using the data from a Hello 70 survey to look for the emission from a helium line. Okay, you may ask why helium? So you don't hear about helium too much, I guess, because when you hear helium, it says, okay, just use 1.4 times hydrogen, then you got helium. So, but the helium has higher ionization energy. Helium-1 ionization energy is 24.6 eV, and helium-2 is 54.4 eV. So helium is able to trace in some very massive O-type stars and even some very rare stars. So it can give us a higher time resolution when we are tracing star formation history. So here we are carrying about a star burst about a tenth or a few tenths of a million years. So here is a nice example of a spectroscopy from a Hello 70 survey. You see booming emission lines. And this is the helium-1, 5878. And this is a zoom in and look at the morphology. It really looks like a local, they call the blueberry galaxies. Not even green pea. It's even bluer than green pea. It's blueberry. Okay. So this is let me talk a little bit about the survey so you got a good idea of what it is. Hello 70 is basically a deep tech spectroscopy survey in CANDLES regions. And we just published the catalog of all the emission line galaxies in this survey. And we also studied the metallicity and the scatter of metallicity in this survey. So two things are important for this survey. It's very deep, so we are able to trace in not strong emission lines, but also some fainty emission lines like the helium and the neon-3. And also important for this work is we are picking up normal star-forming galaxies, not just strong emission line galaxies from CANDLES. So this survey is a representative sample of all low-mass galaxies. So you can see the traces star-forming mid-sequence very well. Okay, so with this survey, we find 10 helium-1 emitters from about 119 galaxies at this stellar mass range and the redshift range. So the helium-1 to H-beta ratio is 0.13. This is basically the maximum ratio you can have based on photon ionization models of H2 regions. And look at here. So this is a helium-1 and helium-1, and this is H-beta. So orange is the 10 detected galaxies stacked together, and blue is non-detection stacked together. So you see the non-helium-1 detected galaxies have a little bit more H-beta absorption, but they also have a helium emission. They are not detected because their helium emission is faint. So actually, the more interesting to us is the blue line, is the stacking of non-detection. And it gives us a ratio of helium-1 to H-beta of 0.06. Okay, why we care about non-detection? Because we care about the whole population, the burstiness of a whole population. So keep in mind that the average ratio is 0.06, and now we go back to build up a very simple model. So this is the burst, and the underlying star formation rate is 1, and you have a burst. Amplitude is A, and you have a duration, which is D. You have a period, which is P. So basically the same model as Danwitz used in 2012. And then we put in, so this is a single burst, and then you add a single burst to your continuous star formation history. And then you can calculate the average helium-1 to H-beta ratio. So here I show you 3 models, and one with the period. So the period between 2 bursts is 15 million years. This one is 30 million years. This one is 50 million years. X-axis is E times A over P, the burstiness. Okay. Now let's compare this result with what we got before. So here, this is a local result from Danwitz, and this is our result from hydrogen to UV ratio, and those are the new results. So of course, depends on the period, the burstiness would be different. But overall, they are quite or broadly consistent with our previous results. So that means the low mass galaxies, they are really bursty. And of course, there are some caveats here. For example, the model is oversimplified. We still need to worry about dust extinction and the stellar absorption and possibly skyline emissions. How many minutes? 6. Okay, good. Okay, so this is for bursty star formation history. Now I'm going to make the U-turn. So think about the low mass galaxies. If they are continuously doing this bursty and temporary quenching, bursty and temporary quenching stuff, how can they be quenched permanently? Because at Redshift 1, we already see some quenched low mass galaxies, a longer time scale, and at Redshift 0.5, there are more and more quenched low mass galaxies. So how were they quenched? What is the mechanism? Okay. So for a long time, people argued that environmental mechanism is the reason to quench low mass galaxies, and we set out to test that by using CANDLES data several years ago. And what we find is indeed, if you compare 2 populations of galaxies, star forming and quenching, so if you compare that distance to a nearby massive galaxy, so here we use a massive galaxy as an indicator of the center of a massive halo. Okay, you will find systematically low mass galaxies are closer to a massive galaxy, which means they are closer to the center of a massive halo. And this is the distance is shorter than star-forming galaxies. And we even had a very naive model to estimate the quenching time scale. So if you assume all galaxies started from here and where they are moving towards the center of a large halo, at the same time they have been quenched, and you take the how long it takes for them to move from this location to this location. The time scale is about 4 gig year. Okay, it's a very oversimplified model, but I will come back to the quenching time scale later. So another thing I want to mention is this method, like a cross correlation, is a very simple and straightforward way to test the models. And here I show you the data and also a model from Candle's mock catalog from Lu et al. Okay, so you can see the model matches the low mass end very well, but it missed the massive end. Okay, this result is very preliminary since 2017 because later my friend Yulu left astronomy and we didn't continue this work. But I have to say, now we have better models, better mock catalogs, so we definitely want to repeat this test. And you may ask why there's a large deviation from massive observed galaxies here and here in observation and in model. So my first impression is because Yulu's model doesn't include AGN feedback. So maybe AGN feedback could be a reason to explain the discrepancy here. Now I'm going to show you another measurement of the low mass galaxies. That's the central mass density, sigma 1. And I guess we will hear more about sigma 1 from Sandy after the coffee break. So here are two examples. This galaxy has low sigma 1, and this galaxy has higher sigma 1. So look at this very busy plot. So different panels means different redshift and stellar mass bins. Stellar mass goes to this way, and the redshift goes to this way. And for each panel, here is low sigma 1, low central mass density, high central mass density, low star formation rate, high star formation rate. Okay. For massive galaxies, with this clearly elbow-shaped structure, and this is not surprising, this is not new, because lots of other people, for example, Guillermo and also Yicheng et al., they also reported and discussed it, this elbow-shaped structure for massive galaxies. Basically, massive quenched galaxies, they have a higher central mass density than massive star-forming galaxies. What's new in our paper is we find a similar result for low-mass galaxies. Okay, low-mass quenched galaxies, they also have, on average, higher central mass density than low-mass star-forming galaxies. Okay, this is for redshift 0.5 to 1, and against stellar mass around 9.5 or below. Okay, so what can this result tell us about the quenching timescale of low-mass galaxies? Again, we use a very simple model. So we assume all the quenched galaxies, they started from here, the blue point, which is the average star formation, specific star formation rate, and the sigma 1 of star-forming galaxies. And they have a mass profile like this. Of course, we know sigma 1, we know total mass, we know the mass in the inner region and outskirt region. We know the mass profile. And then we take a specific star formation rate gradient from Liu et al., also Candle's result, and we use this blue curve for Green Valley galaxies if you want. Okay, here, a very shallow slope, and you put them together to say, hey, now we know the end point. This is the sigma 1 of quenched galaxies at lower redshift. And this is the average location of sigma 1 and the specific star formation rate. So we ask, how long does it take for a galaxy evolve their mass profile from this to this? And at the same time, they move from star forming to quenched. We know the specific star formation gradient. And the time scale is also around 4 gig-year. So now it's very interesting, right? We have two ways to measure time scale of quenching. One is through the kinematics of satellite galaxies falling into large halos. And the other one is through the internal structure of low-mass galaxies. And both methods give us a consistent value. So the quenching time scale is about 4 gig-year. Okay, so that means the quenching for low-mass galaxies is long, it's outside quenching. So it stops the star formation in outskirts, but at the same time, it keeps star formation in the center. And it increases the central mass density. And what are the possible mechanisms? So some quick mechanisms are unlikely, we think, like if any way to quickly remove gas, for example, some tidal stripping. And also, if the quenching mechanism cannot change the morphology of low-mass galaxies, they are not unlikely. So possible quenching mechanisms are starvation, and you cut gas supplies by environment, and it's not all, okay, it's and overconsumption, you have to use up the gas in the center. I think my time is running up. So I'm going to put my take-home messages. So low-mass galaxies, they are very important. And here we studied the bursty star formation history. Yes, they are burst, so good for theorists. And we studied the environmental effect. The quenching time scale is very long. And I don't have time to talk about gas phase metallicity and its scatters. But if you are interested in that, you can ask me offline. And one thing I want to mention is that we really need more direct comparisons between observations and the model and the simulations. And this is a very big reason why we come here to Santa Cruz Galaxy Workshop. Thank you.
Thank you. Questions?
Very nice talk. Thank you so much. Just wondering about, I guess I've got maybe a question and a comment. A comment is, look at a snapshot in one time period. We have to also keep in mind that quenched galaxies may have quenched at a different time period than we're seeing the quenching galaxies today. So that's one thing that we need to be cautious about. The other thing is, too, that that I and my collaborators had found that satellite galaxies, one satellite quenched galaxy, sigma 1 is higher than the star-forming galaxies. We also saw that they were the difference was smaller than for isolated and central galaxies. So, did you? I was trying to look very carefully at your plot there. Did you see that there was a difference? And we had concluded that it was that environmental effects were the cause of the difference.
It's a very good comment and a very good question. So first, let's talk about the difference. So yes, the difference is smaller if you look at here. So those two panels, they are sample not completed. So they are. I'm looking at the black vertical line and this golden vertical line. The difference is kind of comparable or a little bit smaller than for massive galaxies.
Yeah, so yeah, I can see that it is quite a bit different. So how would you explain that?
The smaller difference, we didn't explain that. We didn't compare this difference with this difference. What we focus on is just the existence of a difference itself. And come back to your comment. Yes, when we are using this Coin model, we are not just picking galaxies. We're not just picking galaxies to ask them evolve from here to here. Because we have other things I didn't show up here. We pick up actually galaxies from higher redshift with the typical specific star formation rate and sigma 1 and ask them evolve to lower redshift.
Farhan Hassan, New Mexico State. Thanks for the great talk. I had a question about your median distance to nearest neighbor versus star formation or stellar mass plots. I might have missed it, but there was kind of a U shape, right? Like, yeah. And so, yeah, so it seems like there's a minimum around like 10 to the 9. Like, what is the physical reason for that? Like, should we expect a minimum?
That's a good question. So we suspect that, yes, it has a mass dependence. Maybe this is a transition of a quenching mechanism. So maybe in the low mass regime, environmental quenching is more important, and in the high mass regime, maybe the internal quenching is more important. And that's why I'm very interested in compared to models, because as I showed here, so if you compare result to ULUS model, which has no AGM feedback involved, And you can say, okay, it's good to explain the low mass end, but it missed a lot in the massive end.
While you take a short, quick question, maybe the next speaker can set up.
This is Ife here. So, very nice talk. So I was wondering, because I think originally we saw this sigma 1 or sigma 1 mass relation in phi et al., and it's correlated with the central dispersion. I was wondering if, and this is kind of also related to, say, bolt formation or even like black hole activities, I mean sigma 1 parameters. So I was wondering, for those low mass dwarf galaxies, do you see the same thing? And also some dwarf galaxies, they are small, so their radius can, just be 1 kpc. So does sigma 1 mean the same thing for dwarf galaxy, comparing to what we have found in, established in more massive galaxies?
Okay, I think that's also a good question. So yes, there's difference because dwarf galaxies are small. So maybe more accurately, we cannot call the sigma 1 of dwarf galaxies as a central mass density, but more like the inner region mass density. I don't know if that answered your question, but still we see the increase of the inner region mass density during the quenching. And as back to your question of whether the inner region mass density is correlated with the existence of a bulge or even black hole or AGN. I don't think so, because we stacked some Hello 7D spectra for high sigma 1 galaxies, high sigma 1 low mass galaxies, and we don't see very obvious wind structure or broad wing of oxygen 3, something like that.
Okay, let's thank Yicheng again.